Hello friends of Euler Math Toolbox. I found this question in my YouTube videos. Well, and they did a lot of algebraic manipulation on it, but it's obviously not clear what they did. And maybe they didn't understand it themselves. So this is our integral, sort of integral that we want to study. And it's not a classical integral, obviously, because dx is missing. And this is not a function. Dx is now not behind the function, it is inside the function. And what that means is the interesting question. Well, if it has any meaning for me, it is a classical one, and that is a sum. The integral is just a sum. And I want to show you the definite integral instead, because that has a much more precise meaning. So we want to take a function f of a and integrate simply from 1 to a, like this. Now it makes more sense. Can we compute that? Well, and how? Clearly we have to replace the integral by a sum. So let's do that. What we actually want to have is the following. We want a sum over some xi, which we choose between 1 and a, to the power of some delta xi, which are the dx's, minus 1. So we replace the integral by a sum, and the xi are values between 1 and a, equidistributed, for instance, and the delta xi are simply the differences between the xi. Well, that sounds good, and let's try if that works out. So what we do, we take specific values. Let's take a equals 3. Let's take n equals 10. Let's take the x, the lim space, values between 1 and a, n values. So these values distribute between 1 and 3, and the spacing dx is a minus 1 over n, which is 0.2. That's good. And we can now sum up. Let's first compute it. X to the dx minus 1 can now be computed, which are just these values to the power 0.2 minus 1. And we can sum them up. Now we get a value. Now, what's the meaning of that value? It's a sum, and does it converge? Well, the convergence we can test by, let me first hide that. The convergence we can test by entering a higher number. Let's enter 100 here, and let's shift return to re-execute anything, and we get this number. We get that number, n equal 10,000, and now it seems to converge. Well, to explain the convergence, or what actually is happening here, let's go back to n equals 10. We compute the values y, x to the dx minus 1, which are the values that we had before, and then we plot to the x, y, and let's use a bar plot. Our point plot would also be interesting. So what are we now computing? If we compute the sum of y, we are computing the sum of the heights of these bars. That's not the area, just the sum of the heights. We are summing up the heights of these bars. And then we want to make an area out of that to get closer to the classical Riemann integral. We have to make the area equal to the former heights. So what we do is we just divide that by the value dx. And now we are computing the sums of the areas, because dx times that is exactly what we had before, the y's. So the sum of these areas is actually now what we are computing if we are computing the sums. So let me hide that and like a higher value, it's like 100. Makes much more sense now. So now we are computing these sums of areas, and it looks almost like a function. What is this function? So y is somehow the limit of x to the dx over dx minus when dx tends to 0. And we can ask ourselves, what is this limit? Well, you know now that you either use some analysis tools, or, well, you can use the L'Hopital's rule or whatever. But the question is to impute the limit, the lim, as it's called in datesh, dx to 0 of a fraction, which is x to the dx minus 1 over dx. Let's see if that works. Yeah, this you compute this limit. That looks like a standard question in analysis. X is a fixed value and dx just goes to 0. And what is that? It turns out it is ln x. Let me try to prove that by, or to motivate that by computing a few values. So let's take 3 to the power 0.01. No, we don't have to put that like 3 to minus 1 over 0.001. Wow. What value is that? I claimed it is the logarithm, which now seems probable. Let's take smaller value for dx. It's even better. So actually, the logarithm function is the correct one, and let's try to convince ourselves by putting the logarithm function in here. So plot 2D, the logarithm function in the value x, and we take a red color and add that to the previous plot. You see the red function here is logarithm. It's not exactly the same because it's only a limit, but looks rather good, doesn't it? Well, see that? So what we are actually taking is the integral of the logarithmic function from 1 to a. Well, that's the limit we got if we take higher n's. Just an example, let's take a really large n, and that's almost the same. Okay, this is for less n. Let's take n 1000. So well, we don't see anything anymore, so we take 100. Maybe that's a good compromise. Okay. You see that there is a considerable difference if n is only 100, but the limit is okay. Now the rest of the discussion would be standard analysis and proving that this is actually ln x, which we can insert here. It's a matter of the L'Hopital's rule. but I shouldn't go into these details in this notebook. One should really have a blackboard or something to write on, and I'm not going to do that. It's an exercise in analysis 1 for students, or well, we convinced ourselves that everything works, and in the end we have just the integral of ln. By the way, you can also compute the function itself. So this is an integration, a numerical integration, but you could also integrate that in maxima using exact integration, and you get this function. So now we have this function f, and f of 3, for instance, would be that value. This is the exact version, and this is the answer to that problem. If we take the derivative of that, we get the logarithm. So f of a is the integral over the logarithm, actually, and the answer would be the following to the problem. So we get the integral x to the power dx minus 1 is x times ln x minus x plus a constant. Well, that's the answer to the product integral question. Thank you for watching this video.